So let's discuss now conversion and sources of energy. We all know that we have this different kind of energy, and this is usually in the form of chemical energy, such as energy in the batteries, as well as energies coming from food. And when we eat that food, we can use that ATP to move. Okay? And then also electrical energy can be used by our cars in order for the car to move, and that is kinetic energy. And we also have this electrical energy, which is in the form of electricity, wherein that electricity can be converted into light. Of course, if we are using television, we are using or converting from electrical to sound and light. Now, it is important also for us to have this electricity. By the way, there are two types of electricity. That is a direct current and an alternating current. Once you say it is a direct current, which is discovered by Thomas Edison, and for the alternating current discovered by Nikola Tesla and George Westinghouse, this alternating current, it comes from the turbines, magnets, or simply the electric generators. While this DC or direct current, it can be usually found in the batteries, and then this kind of electricity is usually used by almost all our electronic gadgets. Now, I want to show here the difference between AC and DC. We usually have DC for batteries, and for motors, we usually have this AC. And then, as you can see here, for the motors, we have a pair of magnets, and then the wire is keep on moving. Now, I want you to look on this diagram. For the DC, the flow of electricity is direct, meaning to say it is from one direction. And for AC, it is an alternating current, meaning to say it goes back and forth, back and forth. Now, let's try to visualize the movement of electrons in an AC and DC. As you can see here in our diagram, once you say AC, voltage is alternating. It goes up and it goes down. So from 10 volts, negative 10 volts. Now here, you can see that the electricity or the flow of electrons, it goes back and forth, and there is a cycle. And that is from 60 to 120 hertz. Meaning to say, for every second, it has 60 to 120 cycles. Now, recognize also how the movement of electrons here in the direct current. So from the supply of the battery, it doesn't goes back and forth, back and forth. It just goes in one direction. And here, as you can see, the voltage is constant. So, now, here, we usually have these power plants. And then this can be mainly divided into segments. We have these power plants, transmission substation, distribution substation, and of course, until it will be delivered to our respective houses. Let's focus first on the power plants. Take note that inside a power plant, we can see a common denominator between a hydro power plant, a nuclear power plant, and a geothermal power plant. So here, you can see turbines. And once you say turbines, these are rotating magnets. And then therefore, all of the supply coming from these power plants are alternating current. So here, the water turns the turbine, and then here also from the nuclear reaction, the water in the steam generator will allow the turbine to move, And also for the geothermal plant, the hot water, it becomes hot simply because of the ground, and then it in the form of steam, and then the turbine will gonna move, and then therefore you're gonna have your electricity. Now, I want you to notice also that there is what we call a transformer. What is a transformer? Now, we have these two type of transformer. We have the step-up transformer and a step-down transformer. Transformer is just simply wire are being coiled in a magnet, and then it depends on the number of turns, and it varies now the voltage. So here we have a general formula. We have the voltage in secondary coil divided by voltage in the primary coil equals turns on secondary coil over turns on primary coil. Now here, the primary, we have here the supply, which is 100 volts. When the electricity pass through this, it will gonna be 400 volts. So that is a step-up transformer. So notice also that for a transformer, the more coils it's gonna have, the greater voltage it's gonna produce. So here it is very important to have a step-up transformer. The voltage has been raised up. There it goes now to the transmission substation. And from the transmission substation, it will go now to a distribution substation. The work of transmission substation is to have a more safety environment when we are using electricity. And we also have these distribution substations so that it will have a safer distribution supply of electricity among the household. After the distribution substation, we have also this common thing that we see in our streets, and that is called as transformers. I know you see that on your streets. You could see these step-down transformers, and it simply controls the electricity. Now, take note that in power plants, we usually have this 12,000 kilovolts. It's a very high voltage. And then travel into the high voltage transmission line. Before it will be distributed to our houses, it must go first to the substation, wherein it will be stepped down. From 400 kilovolts, it will now become 13 kilovolts. And then we could have the 13 kilovolts down to 240 volts by the step-down transformer. A step-down transformer, we have to reverse the coils. So from primary coil, which has many coil, let's say for example here we have 50 turns, and then this wire, it has only 10 turns. So from 1000 volts, it will now become 200 volts. That is the work of a step-down transformer. So here it's now ready to be delivered in our houses. And we have these different electrical devices such as the meter readers, the fuse box, and here in the Philippines, we have 220 volts supply in our houses. Okay, so meaning to say when you plug in some appliances, they are 220 volts. Take note that what we are using is AC electricity, alternating current. Now, there are devices that requires direct current. So meaning to say, when we have this AC load, there are devices that it needs to be converted to DC. We have here refrigerators, monitors, DVD players, printers. So meaning to say, from AC load, the electricity must be converted into DC. But there are some appliances that allows AC only, so we don't need to convert it. These are blenders, electric fans, and hair dryers. Notice also that this AC load use AC, and then therefore these are usually motors. And take note also, we have these devices that can be plugged into AC or DC. Now, if the supply is AC, how can we use it now as a DC? Well, we could use AC to DC components such as the AVR, automatic voltage regulator. You can usually see that outside your computers. And also, we have this inside of the component. So if you, for example, if you open a radio or open a TV, you can see here a rectifier. A rectifier is a device inside our component for us to convert this AC supply of electricity to DC supply. Now, there's a question here. What if I have 110 to 120 equipment voltage requirements? Say, for example, you bought a refrigerator from Japan. It only requires 110 to 120. And then, therefore, you will use this step-down transformer. So you can see this at this device at the back of your refrigerator that is a step-down transformer so that you can use your household electricity, which is 220, and that be converted into 120. So this is how the step-down transformer works. It's just like a coil of wire surrounded by magnet, and then a step-down transformer. The diagram is like this. There's a core, and then the wire in the primary, it has lesser wire in the secondary coil. So the primary has more coil than the secondary. Again, we have this general formula, which is voltage in the secondary coil divided by voltage in the primary coil equals turns on secondary coil over turns on the primary coil. A step-down transformer can also be found inside electronic devices. We have also the transformer for us to use a smaller voltage. And also, like for example, our chargers. The cell phone chargers, it will already convert the 220 volts AC from our sockets directly to 9 volts and as well as DC. That is the work of our cell phone charger. Now, how is energy efficiency calculated? The energy efficiency of a device can be calculated using this formula. Useful output energy divided by total input energy. Useful energy is usually measured in joules divided by joules. Therefore, energy efficiency does not have any units. It is a number between 0 and 1 which can be converted into a percentage by multiplying by 100. Let's have a sample problem. This filament bulb is supplied with 100 joules of electrical energy, which it converts to 45 joules of light energy. We have here the given, which is 100 joules of electrical energy. Then it will be converted into 45 joules. Then the first question here is, how much energy is wasted? That is, total minus the useful, 100 joules minus 45 joules, and we have here 55 joules. In what form is the energy wasted? And that is in the form of heat. So what is the efficiency of the bulb? Now remember, it is useful over total for the efficiency, and that is 45 over 100, and then therefore that is 45%. And that ends our conversion of energy from power plants to electrical.